Okay, we are going to start today the mechanical design of battery pack. But before starting this, let's review what we have done in the last class. We have started with what are the needs of a battery pack design. Then we categorize into different aspects of a battery pack design. What we found, there are 4 aspects what we should look upon: the electrical design, then mechanical design, then thermal design, and the last BMS and embedded system. What we did last class is about electrical design: current, voltage, capacity. We calculate from the electrical point of view, from the electrical design. That's the first step. For making any battery pack, you need to find out what is the capacity, what is the voltage you require, what is the current requirement. Now, once you have done that, then what are the issues can come? So, we have seen several issues, like there should not be a voltage drop. If there are parallel paths, since current demand is huge in EV, so we have to most of the time we have to go for multiple paths for the carrying over the required current, and each of the paths should have the equal resistance if we are designing it for the equal current. If we are dividing, what I have not talked about, let's suppose if we design for the different current, so again the same formulation, L1 by A1 should be different, should not be a constant, it could be some different values. And based upon that, we can also design, if I want in different parallel paths, if we want to put different currents, that is also possible, the same formulation. But ideally or in generally, you would like to have the same current from the all paths to reduce your design complications. Then we have talked about other various aspects, like if there is a short circuit scenarios, how to design a bus bar. Other than the current, what is the other important factor in the designing of the bus bar, which is thermal aspect. So any current carrying capacity is mostly limited by the thermal aspect. Then also we have talked about voltage drop in the harness as well as in bus bar. Once again, short circuit, then parallel current path, and then we concluded what are the things we require for electrical design of a battery pack. So today we will start the mechanical design of a battery pack. We will start from the same problem where we have started in the electrical design, where we have found capacity, current and voltage. From the similar problem, from the same problem we will start further, and then we will try to find out what would be the weight of the battery, self weight, then what are the other forces that could be acting, what are things we need to take care during the mechanical design. And then later we will also talk about the one of the most important aspect of a mechanical design is the vibration, and then we will close this part. So cell is the fundamental block of a battery pack. So let's understand the mechanical design of a cell. When I say mechanical design of the cell, how it is going to impact in making a battery pack. So various type of cells, what we have seen in the last time: cylindrical, prismatic and pouch cells. This is what 3 form factors is being used universally. Now in cylindrical, you have a small cylindrical, large cylindrical. In prismatic also you have a small prismatic, large prismatic. Even in pouch you have various capacities. So when you say cell casing for a small cylindrical or large cylindrical, mostly it is a metal. Now good thing about this cylindrical cell is the pressure during expansion or contraction is uniform over the surface except top and bottom. So this is basically being made from the metal, mostly aluminum. Then when we go for prismatic cells, so it could be either semi-hard plastic or a metal. When we say metal, it's mostly aluminum or aluminum alloys. Pouch cells, again semi-soft plastics or aluminum soft bags. Connections, how do we connect these cells together in a battery pack? When we say small cylindrical cells, mostly it is welded. Even for the large cylindrical cells, it's mostly welded joints. The bus bar what we place is mostly welded. Prismatic cell has both the options. The terminals can have a threading option where we can put a nut and connect the bus bars, or the other option is that we can weld also. But as soon as we talk about welding here, then that welding is not easy. If this is the large form factor prismatic cells, in that case, we don't get much option other than the laser welding. However, for smaller packs, where we don't have a lot of current carrying requirement in bus bar, resistance welding or spot welding also helps, and actually that is the most preferred method. In pouch cells, again, either it could be a threaded one where we can tie it with a bolt and the bus bar connection, or most of the places it's a laser welded, because generally the form factors capacities are much more than the cylindrical cells. Now retention, again expansion or contraction, both. In cylindrical cells, by virtue of its shape, you don't require any additional mode or method for expansion or contraction during charge or discharge. In prismatic cells, yes, you require. Pouch cells also you require. Why will require? We'll find out later part of this discussion. Field replacement, if you design it in keeping in mind that okay, we may have to replace into the field also, possible. But generally in small cylindrical cells, when you go for the high capacity pack, so you have multiple numbers of cells in parallel. So in that case, even 1 or 2 cells doesn't reduce the capacity drastically, maybe few percent, 1 or 2% or 5% or 7% or 10%. So you don't want to go and replace the cells. It's difficult also because you have a complete bus bar at the top, bottom, and then it's encased with the several other layers. It's difficult to take out 1 or 2 cells and replace it. Large cylindrical, yes, it is possible, and you can do that also by again you have to think this during the design phase of the battery pack itself. Prismatic cells, yes, it is possible, but we need to be careful during the designing itself. Pouch cells, since most of the places it is a laser welded joint, it becomes difficult, because once you remove one cell, basically you have to dismantle the whole battery pack and then only you can replace one cell from that. But yes, it is possible, but generally people don't do that. It has to come back to the service center then only. So in the field it's difficult. So that's why it is put upon not possible. Delamination, if you want to open up the cells and delaminate and wanted to check that your cathode, anode and everything is intact or proper or not, or if something has gone wrong, can we do the factory fabrication once again? In small cylindrical cells, it is not possible. Large cylindrical cells also it is difficult. Large form factor of prismatic cells, it's possible. In pouch also it is possible. Now compressive force holding. So if you see third and sixth is just opposite to each other. So by virtue of design, if something works for third, it will work for sixth also most of the time. So it's a very good in cylindrical cells, not so good in prismatic cells. Pouch cells, it's very bad. Safety, considering third and sixth, is good for cylindrical cells. Moderately okay, because you have a metal casing. Most of the time you have a metal casing in the prismatic cell. So it's a moderately good. However, in pouch cells, you don't have any hard casing. So it's not so good, it's a poor. Heat shrink wrapping. In cylindrical cells, yes, you can do. You don't need to, but if you want to have extra layer of insulation, yes. In prismatic cells, depending upon the casing, if you have already semi-hard plastic, you don't want to have it. In aluminum also, based upon your design, do you want to have heat shrink there or not? It's on you, but it's possible. In pouch cells, we don't do that, because it's basically a soft bag. We don't want to constrain it further with anything other than the proper constraint method. So it's all about from the cell to pack, what are the things you need to worry about on the material side. Now let's start from the same problem what we have started. So consider a two-wheeler electric bike designed to have a range of 70 kilometers. So when I am reading this question, when I am saying about this question, so these questions require from first to fourth chapter, and then the fifth chapter 5.1 electrical design. All those things are required here. So consider a two-wheeler electrical bike designed to have a range of 70 kilometers. A normal range of two-wheeler is around 70 to 80 kilometers. Anything between 50 to 100 kilometers works well. Now, these two-wheelers consume 16.5 watt-hour per kilometer. That means on an average, for 1 kilometer of running of this bike consumes around 16.5 watt-hour per kilometer. Now, considering the depth of discharge, DOD, why DOD is required? Is to prolong the life of the battery pack. So, at 80% DOD, design a battery pack of nominal operating voltage 60 volt. So, what is defined here is the range, correct? And then also it is said what would be the consumption per kilometer. So, if I multiply per kilometer consumption with the range, energy consumption with the range, then that would be the energy requirement of the battery pack. Now, the second para of the question says the depth of discharge should be only 80%, not more than 80%. Then my initial pack capacity has to be increased so that whatever energy I require for 70 kilometers should be available. That means even the battery pack capacity is large, but my depth of discharge is low, I may not have available energy to run the vehicle. So, depth of discharge, we have to consider a factor here. Now, operating voltage is 60 volt. So, we will see NPTEL-NOC theory that how many cells we require in parallel, how many cells we require in series. So, first we have to find out how many cells are required in series. From the voltage, we will get how many cells are required in the series. Then we also have the capacity. Now, this 16.5 watt-hour per kilometer is the energy consumed by drivetrain. Auxiliary systems has not been considered. So, the third paragraph of the question says the power consumed by auxiliary system is 2 watt-hour per kilometer. So, what would be the total power consumption per kilometer? 16.5 plus 2, so 18.5 watt-hour per kilometer. Okay, and this is a typical two-wheeler. I think it's Ather. Yes. Okay. So, Ather, one of the model. So, if you see what is our total energy consumption per kilometer is 16.2, 16.5 plus 2, that is 18.5 watt-hour per kilometer. For 70 kilometers, so multiply with 70, you get 1295 watt-hour with 80% DOD. So, you have to divide by 0.8. So, my pack capacity should be 1618.75 watt-hour. That is my pack capacity, it's supposed to be. Now, we have a cell, the dimensions of the cells are given here. So, and this cell's nominal voltage is 3.65. So, for making a 60 volt pack, number of cells in series, how much it will be? 60 divided by 3.6. So, it comes 16.43. So, we cannot make a 16.43 cells. We can either make 16 or we can make 17. So, it's good to have 16 cells because that also fulfill my requirement. It would come around something like 58.4 volt, something like that. So, that's fine. So, we select 16 cells in series. Now, number of cells in parallel. What is the capacity of this cell? Is 14 Ah, correct? That's what we discussed last during the electrical design of the battery pack. So, 14 years. So, how many cells we require in parallel is 1.97 cells, but we cannot put 1.97 cells. So, what we can put is a 2 cells. So, 2 parallel and 16 series. So, that's how it comes. So, what is the battery pack parameter? 2p16s, correct. So, total number of cells, how many cells we require to make this pack is 32 number. What we have decided to go with the 2 modules, that means 2p8s, 2p8s, and then we'll make it in series. So, the number of cells in one module, how much it becomes? 16 number. Now, total weight of the cell. Since now we started with a mechanical design, so now we are worrying about weight, force, pressure, all those things. Now, the cell specification is here given 3.65 volt, capacity 14 Ah and weight is 0.32 kg. Now, the total weight in both the modules together, that means in the whole battery pack, that comes out to be around 10.24 kg. So, as soon as I start designing, first of the things what I have to look upon, what is the weight of the battery pack, and then based upon that only we can start looking for what are the things we require. Before moving to the mechanical design, let's understand what are the fundamental forces can act on anything. And obviously, when I talk here, it's more about battery pack. So what we have, stress strain theory. Various type of loading which can act on any object are only limited. What you can have? Compressive force, then you can have tension, then you can have shear, torsion, and finally bending. So these are the 5 types of fundamental loading on any object. Now moving next, what is the stress? Stress is the internal resistance offered by the body for any external factor. So it's defined as stress is the internal resistance offered by the body to the external load applied to it per unit cross-sectional area. Pressure also has a similar definition. So this stress is nothing but F by A naught, where the sigma is saying stress, Newton per meter square, or that's also defined as a Pascal. But pressure and stress is different. F is the force applied, the total force applied, and the A naught is, or A0 is the cross-sectional area over which the force is getting applied. When you try to pull or push, that means either you try to compress or you try to expand. The resistance, internal resistance will try to resist that expansion, but something will change there. It could be length, it could be width, it could be both, and that's how the concept of strain comes. So strain is deformation of displacement of the material that result from the applied stress. And what is the applied stress? Is basically force per unit area, cross-sectional area. So let's suppose the initial length is L0. After the application of tension or tensile force, it has elongated to L. So what the differential difference, or what is the difference, is dl or del L. There is a possibility that it gets in this direction. Instead of elongation, compression can happen, but let's assume that's negligible right now. So in that case, epsilon is nothing but delta L by original length, and this epsilon is nothing but strain. L is length after the load is applied, L0 is the original length. When you move further, this what we have talked about mostly when the force is applied in one direction, but generally that does not happen in real life. It can be a compressive force, it could be a tensile force, it could be a shearing force, it could be a torsion, it could be a bending. Any of this is possible, but the strain remains same. When we talk about further, we change the terminology to stress, then deflection, all those things comes. But if you come back, these all are related to these 5 fundamental forces. Now, what are the forces on a battery pack? What we have calculated right now is the weight of the assembly of the cells. I am assuming there is no other weight right now. So what are the forces on a battery pack? If you see, the end plate will have a bending force because you try to push out, but it is constrained at all the edges. So it will try to bulge out like this. So it's a bending force on end plate. The next is the bending force on the base plate. And why? How that is happening? Because of the weight of the cells. If let's assume no other forces are acting, so it's because of the weight of the cell, the base plate gets a bending force. When you are connecting this plate and this plate, then this through this side strips, then either it would be in tension or it would be in compression. On the bus bar or between two cells which is connecting each other and held by a module enclosure, will get a shear force mostly. So what we have discussed in the earlier slide, 5 fundamental forces: compression, tension, shear, torsion and bending. Except torsion, even torsion is also present, but for simplicity we have not shown you here. So all types of forces acts on the battery pack, and then we need to find what would be the force, what would be its effect, stress, strain, deflection, and then we have to select some material, connect it together so that everything should be within the limit of that material or within the limit of my design. How to do that? So we'll start with base plate, design of the base plate. So what we see here, we know the cell dimension, length, width and thickness, all the 3 things we know. Now we also know the way we wanted to keep the cell. We wanted to keep the cell in such a way that it should not be very long, it should not be, the width should not be very wide. So we have decided that let's make 2 modules. As soon as we decided the 2 modules, now we know how to, after putting a sufficient clearance between the 2 modules, we know what would be the length and the width of the module. As soon as we know what is the length and width of the module, so 2 dimension of the base plate is known now. So the 2 dimensions, this dimension and this dimension is known now. What is not known is the thickness, and the thickness depends upon what would be the loading on that plate. Assuming right now it's only the self weight of cell, let's design that. The following assumptions or conditions: it's a continuous rectangular plate of constant thickness, simply supported on all the edges, and uniformly distributed weight. So when I am putting the stack of the cells together, I am assuming that the weight is uniformly distributed over the base plate. So what is the length? 285 mm, breadth 138 mm, thickness we don't know, we need to find out. How do we find out thickness? The area of the total surface is 39,330 mm square. So what is the load? It's the total force by total area, and that comes to 2.554 into 10 to the power 3 Pascal or Newton per mm square. Now, before going to find out the thickness, we have to find out which material we should select. And when we say which material we should select, so there are several methodologies to find out which material we should select. We'll talk one of those methodology now and try to understand how does it help in material selection. Okay? So any question till now?
At the very start of the first question, you mentioned like DOD of 80%.
Yes.
Do you start from full charge like full 100% SOC, or will you start from 80%
No, it's
SOC?
based upon the cell characterization. That's what we studied in chapter 1, chapter 2, chapter 3 and chapter 4, mostly in chapter 4. So based upon the cell characterization, you find out what would be the best DOD for you.
Okay.
And once you have selected, then you have to just bring it here
Okay.
in the design.